So hello everybody, my name is Stefano D'Angelo. I am the founder and CEO of a small company in Italy with DSP Consulting. And I'm doing this weird presentation here about LEGOfying audio DSP engines, which actually means making DSP development scale to increase productivity a little bit. So my criminal record since it's the first time I'm here, I just want to introduce myself very, very briefly. I studied at the Polytechnic University in Turin, taking a master's in computer engineering. Then I participated to some open source projects in the meanwhile. I did my PhD studies at the Aalto University in Helsinki, Finland, in acoustics and signal processing. Then I went working at Arturia as a DSP engineer from 2015 to 2017. So if you have tried the Buchla Music Easel synthesizer, you know who to blame for the DSP part. Then I started freelancing from home in Italy. And then last year I founded my own company, which still continues this freelancing stuff and other stuff as well. My clients include big companies, actually, like Arturia, Neural DSP, Dark Glass Electronics, ELK. I'm the author of 18 scientific publications so far, and I'm officially recognized as an expert in this domain in Italy and France. Enough with the bragging. Let's go on the actual stuff. Okay, so let's say that we want to just implement a volume control. We know that the formula is this thing here. So essentially, we just scale an input signal to obtain the output signal, and we could implement it more or less as shown here. So essentially, here we would have a rather normal process function with the only peculiarity that this k parameter is passed as an argument to the function. But I mean, you could use any other kind of solution for that kind of thing, and you would apply the formula as it is, and you would have two issues here. So the first issue is related to the so-called Weber-Fechner law, or whatever it is called, because I don't know the pronunciation to this thing, which is let's say it's a law that is used in psychoacoustics, which essentially says that the intensity of a stimulus is logarithmically related to the perception of such stimulus. So essentially, for example, if a gain of 10 times gives us a perception of twice the loudness, then to obtain a perception that is 3 times the loudness for a signal, we have to apply a gain of 100 times. In other words, or actually in images, if we vary the stimulus linearly, we get a logarithmic perception increase. Or otherwise, if we vary the stimulus in an exponential fashion, we get a linear increase in perception. But, I mean, we could just use an exponential to fix the problem of having, if we want a linear perception increase, that wouldn't work well for a very simple reason, that an exponential is never zero. You cannot reach silence, so we cannot just apply that. One simple solution is to offset and rescale, so that we apply an offset and scale the thing so that we can actually reach silence, and we have an exponential mapping. A little bit better solution is to also force a midpoint value, so that when our control is at 0.5, we know exactly what point we are hitting. And indeed, exponentials are determined by having 3 points, by choosing 3 points. Number 2 is more general and natural, also because that's more or less how potentiometers in circuits are meant to work. Like if you buy and logarithmic, they call it, potentiometer, they are usually classified by midpoint value. So we can try to fix this thing. Instead of using k, we use a function of k. And this function of k, if we impose a midpoint value of 10%, minimum value of 0%, maximum value of 100%, is given by this formula here. I spare you the mathematics. So essentially, we can implement this thing, and it's pretty straightforward. The only thing that we give a little bit of attention to is calculating this thing outside of the audio loop, because it would be useless inside. But still, we have another issue: zipper noise. So essentially, since the parameter varies at the rate that is much lower than audio rate usually, we have a noisy stepping effect, which is very characteristic of these sort of algorithms. That's what we actually get by not applying any smoothing, and if we smooth the parameter change, we get something like this. So essentially, we want the second thing. I will spare you again the computation of the filter or whatever mechanism you use for that, and just show you a final version using a one-pole filter. The thing complicates a little bit. I will not go into the details here, it's useless, but essentially what we are doing now is just applying, filtering out this V value that we computed before using this filter, and we can compute the coefficient beforehand, and we have one state, which is the state of the filter. This is not optimal, can be also improved sonically, whatever, but this is already good enough in many cases. So what we've seen is a very stupid example, but there are many considerations that can be done using this example as an excuse. The first thing that I want to say is that coding in all of this is very marginal. And that's the case in many DSP algorithms when you go and actually develop them. Actually, I found that there is a book called Programming is 10% writing code and 90% understanding why it's not working. I add to that music DSP is 10% programming and 90% deciding what to program, which means that coding is 1%. So I cannot stress enough the work done for documentation and communication with other people in other teams and so on, because otherwise, looking at the code, you understand most of the times about nothing. Takeaway number 2, yet coding is essential. We cannot skip it, we cannot do it poorly. So if we look at the example that I've shown already before, there are some things that we can already say about the way it's being programmed. First thing is that we are bound to real-time programming constraints, so we have to take care of the execution time of these algorithms to be deterministic. Then we have a notion of update rates, which is non-trivial for non-DSP programmers, which means that we have signals that vary at a lower rate than other signals, and we need to take that into account. We should use sensible APIs. I hope this is a good example. It's more or less like most plugin APIs work. It's very similar to BST, for example. And in this case, it's not very evident, but many times you have to have some serious knowledge about how the target platform works and how the compiler works. Takeaway number 3. Math alone is not everything, and I will leave you 10 seconds here. That's mathematically not meaningful, but okay, so the first thing to notice is that we have used knowledge from many different fields already. For a very simple example, we used the Weber-Fechner law, which comes from psychoacoustics, and the log potentiometer mapping comes from electronics. But at the same time, we also have used domain-specific knowledge. We have recognized and tackled the zipper noise problem. We had to choose and apply a smoothing strategy, and we had to implement the thing. So essentially, if you want to be a DSP developer, you need to have T-shaped skills. Essentially, you need to know a little bit of everything and a lot of one thing that's DSP, or maybe two, also programming. Again, yet we cannot discard mathematics. We need to be math-grounded. And I just learned that this is sheep grounding in English. I didn't know that term. By the way, that's the Costa Concordia thing in Italy. Okay, anyway, we have used log scale, we have used exponential mapping, we have used an IIR filter. The coefficient was derived using the impulse invariant method, which is a very specific method for implementing low-pass filters, if you're not familiar with that. And there was also some DC gain correction on top of the impulse invariant method, only in this simple example that we've seen. Takeaway number 5, music DSP is hard. As I said many times already, we've seen really simple stuff. It's not like that all the time. We can have, when developing DSP algorithms, a lot of math complex involved. We have temporal recursivity in many cases, which makes debugging extremely hard because your input signal, all of it becomes an input to the algorithm. So essentially, if you process 1 second of sound, you have 1 second of samples to take into account to reproduce the same state of the algorithm itself. We have numerical errors, which are due to finite precision, and you need to deal with those sometimes. Time-varying stability problems, where you vary parameter values, they can create lots of issues as well. You need to know a lot about special techniques like circular buffers, FFT implementations, and whatnot. Performance is a major concern. And communication of perceptual qualities between, I don't know, for example, sound designers and DSP developers is quite hard many times. Like when they come and say, I want the sound a little bit more crunchy. Yeah, sure. So this is what you want to do most of the times as a DSP developer. Now let's take let's ask, I ask myself this question: can the market afford all of this complexity, like money-wise? So let's look at money numbers. According to the NAM Global Report of 2020, the whole market is worth $8 billion in the USA and $17.5 billion worldwide. And the DAWs and plugins sector accounts for about 4.6% of this market. So we are talking about 365 millions, and I extrapolated to 800 millions worldwide. Let's compare with other markets. First, the GDP of San Marino, which is the smallest European country in terms of GDP, is already bigger or comparable to our market, and there are only 35,000 people living there. The global plastic bag market is bigger. The global smoked salmon market is even bigger. The global hand tools market is way bigger. The global sex toys market is immense. The global database management system market is even bigger. So we are, between screwdrivers and smoked salmon as the whole music technology market goes. Then I tried to examine a little bit the offer of plugins, essentially, by looking at the data on KVR. Essentially, they have a database with all the plugins that exist, more or less. At least most of them. And then they have a marketplace. And the first thing that's very evident is that half of the market is actually dedicated to soundware stuff. Presets or samples, stuff like that. Of the remaining part, a little small chunk is about hosts and mobile apps. And then we have effects and virtual instruments, half of which are free. On average, indeed, half of the products that are on this market are free. A brand has, on average, 4.5 products on the market. And each paid product, on average, paid products make about $90,000 a year. A brand makes about $200 a year on average, which need to pay for a lot of things. It might look like a lot of money, but it's not. At least for an Italian, it looks like a lot of money. You have fixed expenses, administration, management, development, IT, legal, marketing and sales, post-sales, distributors, investors' dividends, eventual loans, taxes, possibly also save some money after all of that. There's little money. It's very evident. But averages can be explained a little bit better with this equation that I call the Trilussa equation, after the name of an Italian poet from the beginning of the 20th century. He essentially said that if a person eats 2 chicken and you eat no chicken, then you, on average, eat 1 chicken each. So if you go and actually look at the distribution, we have that about 8% of the brands make about half of the paid products, which looks suspiciously close to what the Pareto principle says. The Pareto principle, for those who don't know, is a principle that says that with 20% of the effort, you get 80% of the reward. Or the 20% of the people make 80% of the revenues, let's say. So if that is true, it means that 80% of these brands fight for 20% of the market share, which means that the smaller brands make about $50K a year on average, which means they're hobbyists, essentially. And this confirms the fact that there are very low barriers to entry in this market. Let's look at categories too. So I went and checked how many product categories are classified in Plugin Boutique, the Plugin Boutique distributor. And there are about 50, but you know, inside these 50 categories, there are products that are not in direct competition. So I just made a random estimate and multiplied the thing by 2. So let's say that there are 100 categories of competing products. That means that in each category, we would have an average of $8 million of revenue with 180 competing products, 90 of which are free, 45 of which make less than $51,000 a year, and 45 make more than that. So that's what the distribution looks like. There are like 20 products in each category that makes, well, good money or money, and the rest of them, no. So the market seems to be tiny, poor, saturated, and unattractive. If you started doing audio, you're screwed. You do it for passion, not for money, okay? So if you want to survive and thrive as a company in this space, you should ask yourself the obvious things, but very clearly, like whether a product is worth making, which means how much, you need to know how much, to ask yourself how much it will cost and to make and sell. If it will be useful, desirable, what problem will it solve? Will customers buy at what price? How long will it sell? What is your value proposition? Will people prefer to crack it rather than pay it? Are there better free alternatives? That's often the case. And then not only you need to ask yourself about today, what happens today, but also about what happens tomorrow. How will the market change? Like, for example, what will the future bring in the offer side? For example, we know about this sound wide thing. I don't know for good and bad how this will go. We will see, but it's relevant in our market, for example. Plus, we know that in the current situation, we have a huge stagflation risk, and high interest rates are not a good sign for employment and stuff like that. And then we need to also ask what the demand is, in the sense that what if new platforms, technologies, usage trends emerge, and what can we do to adapt to them as fast as possible? So essentially, we want to ask ourselves how to be competitive. And I came up with 5 simple things that are probably good sense. Like, one is improve product quality or desirability, increase productivity, cut time and costs, rely on flexible technologies, which means cut future time and costs, and spread the word. That means investing in advertising, marketing, sales, and so on. Of course, if you have better ideas, please tell me. Okay, so now I will move randomly again to more anecdotal evidence, in the sense that that's what I experienced so far. One thing that is very evident to me is that there are few and hard to access sources of information for people who want to work in this field, because it's small and it's not often the case that people share their knowledge around. At the same time, there are few and hard to use domain-specific tools. Again, I think it's the same reason. There is few people who work in the field and there's no incentive to develop them, economic incentive. There is a strong tendency to follow external trends that maybe sometimes have really nothing to do and bring no value to our sector. And then the worst part, like, it happens very often that, especially in bigger companies, managers and executives come from other sectors, which means they are little aware of domain-specific issues. There are huge difficulties in evaluating work of people who actually do DSP and assessing the responsibilities. It's always, he did that. You know how it is. And the easiest path to increase profitability becomes very often cost-cutting because of this lack of understanding, which also means that the work offer adapts to the demand of work, which if the demand is unprepared or unskilled, will prefer people who are paid less instead of people who know more or less what they're doing, which means that researchers are kind of pushed on the side and have very little opportunity to collaborate with many companies. All of this, to me, means that we also have a problem of efficiency and effectiveness in what we are doing. So, I was saying this stuff before. And if you ask me, I'm maybe biased because I'm a tech guy, but I think that technology can help on 4 out of 5 points on, on how to be competitive. So let's examine what's available for us. We have some tools which mostly come from other areas, but they're very useful for our cases, for use cases as well. Some of the tools that are very good, in my opinion, that we can use are computer-aided algebra systems, like Maxima, Mathematica, Maple. Numeric computing, we have Octave and MATLAB, which are excellent tools. For visualization, I personally use a lot GNUplot and Sonic Visualizer, which are both open source and free. For circuit simulation, we have excellent tools. We have SPICE and these other things that I don't know how to pronounce. Recording and editing, plenty of options. Data extraction, I use a tool called Webplot Digitizer, which is probably pretty much unknown, but it's very useful to extract data from images. We have frameworks to develop plugins, and that's about it. If we actually go and look at what tools would be useful for DSP development in itself, we lack good domain-specific languages, at least until yesterday, because I've seen the presentation of C major, but we used to lack them until yesterday. We lack tools, automated or interactive tools to design algorithms and parameterization strategies for plugins or whatever you have. There are some in some specific cases, but overall, we lack them, in my opinion. We lack DSP-specific debuggers. Sometimes it's just horror. I feel, this is controversial probably, but I feel that also we lack some good visualization tools. For example, there is this Sonic Visualizer tool which was developed here in London at the Queen Mary University. It has some excellent spectrogram visualization. It has excellent spectrogram visualization, but and it also has an SDK to develop plugins for visualization and analysis, but the plugins that have been developed are very few. And in my opinion, not very useful for the kind of DSP that I do, which is mostly virtual analog stuff. We lack specific sound analysis tools also, in my opinion. Then going to a higher level, I've never seen good DSP libraries, I'm sorry, but things that are actually usable in products. Everybody develops their own, but we'll talk about it later. Or tools to develop your own products, like in a rapid application development paradigm. There is some stuff, I know, but so far it's not very convincing to me, again, to me. So for me, for my tastes, I would say that the generic tools that we have are okay. Generic in the sense that they come from other fields, but the specific ones, not so much. So, how does it work in companies? How do companies deal with this stuff? They let some DSP guy develop some stuff. They reuse as much code as possible. They profit. But if you look at it, number 2 is not stupid. Music DSP, as we said, is hard, so reusing stuff is a good strategy overall. And this can be done in many ways, one of which is largely predominant, and I call it the software engineering way. So essentially, you make a library of DSP modules, usually using an object-oriented programming paradigm. And it's, as I said, by far the most common approach. And if you're not familiar with object-oriented programming, I can explain it in 4 sentences. Essentially, you have a class, which is an idea of an object, like a class of the computer, the door, I don't know, anything, but it's not a specific object. Then we have an instance of a class, which is the specific object. Then we have encapsulation, which means you have an interface to interact with the object, but that shields you from knowing the details of the implementation of some such object. And then we have composition, which means that an object can contain other objects. Usually general purpose languages, low-level ones, are used for developing plugins and so on. The good. They usually provide object-oriented programming support, or it's usually easy to program in such a fashion. They give you a lot of flexibility because they're used everywhere for everything. The performance is usually very good. They're very portable. by themselves, and they are very widespread in the industry. So those are good characteristics to have. The ugly part. They're conceptually distant from our specific problems, from the problems of our area, and force you to have a lot to learn before you are able to develop in a way that doesn't suck. So there is a lot to know for developing very specific things. This, in my opinion, leads to a couple of things that I've seen often happen, like people tend to use lots of abstractions, over-engineering and so on to fight for this lack of focus that you have when programming on these languages. And this usually makes things not better, but worse. Plus, if you actually go and check how these languages were developed and designed, you see that they were designed mostly to develop simple code that works on complex data, which is the exact opposite of what we do in DSP. We have very complicated code and very simple data structures. And at the same time, we have that the control flow part of the language is predominant over the data flow part, which is, again, something that is completely different from what we want to do in DSP. The bad part. These tools are general purpose by design, so there is no specific API built in the language or something like that to do DSP or whatever, which means that everybody can develop their own API and whatever, which is kind of good in a way, but it's also kind of bad because it leads to problems of incompatibility, inhomogeneity in the APIs and so on. And this open-endedness also makes it very difficult to build tools to test algorithms and stuff. Plus, usually we are kind of bound to buffer-based processing, which is not ideal when you want to implement feedbacks, which might not be a concern for you, but still. Another thing that I want to point out is whether encapsulation in itself, so the fact that we hide the implementation details, can be harmful. And unlikely it can be, because hiding details makes usage easier, but when we talk about sound and sound quality, we are talking about something that is rather fuzzy and delicate. Fuzzy because it's hard to define, and delicate because it depends on so many things. And usually music DSP is such a low-level thing that even details are critical, and we don't want to have everything hidden from us. So usually the two things that you can do is find a sweet spot balancing ease of use, complexity, and reusability when developing a DSP library of components, and try to embrace modularization as much as possible so that you give as much control without renouncing to encapsulation to the end user of the library. So, what music DSP libraries are available today? Well, code is precious because music DSP is hard, and the market is tiny and poor. So what happens is that companies just reinvent the wheel and keep the stuff for themselves. There are a few generic music DSP libraries or part of libraries like in JUICE or the STK, the Synthesis Toolkit library, but they're not exhaustive. There are some highly specialized ones like Rubberband or the Z-Plane libraries for pitch shifting and time stretching and so on. But still, I feel that the commercial licensing and business model behind those projects is somewhat problematic in many ways. Another thing that happens that's related to how development is done today is that it's the problem of the sandwich junior audio programmer, which means, I will explain. This means that in order to use a DSP library, you need a programmer. You cannot let it be done by a sound designer. But you still need to cut costs, so you don't want the music DSP people to do it. So what you do is this. You have DSP engineers on one side, sound designers on the other, and you put these poor souls, these junior programmers in the middle, trying to combine the things together. And this is a technology-induced cost. This only happens because we are using general-purpose languages. But there are other ways. One other way is the sound design way, as I call it. But this is, we will talk about. Okay, so the sound design way is, this is pure data. People know Max MSP. Essentially, a sound designer can build an audio engine by himself by combining blocks together and stuff. In this case, we have that a class is a box class. An instance corresponds to a box, Encapsulation is the input-output interface of each block, and you can sub-patch, so you also have composition. So you have the essential of object-oriented programming already built into this metaphor. On the other hand, you renounce to data structures, dynamic memory, code recursion, and control flow, usually. So how do these systems compare to general-purpose languages? They're usable by non-programmers, which is a huge result, a huge feat. The communication between the DSP guy and the sound design guy can improve enormously because the DSP, the sound design team or person is much more autonomous. Homogeneity and compatibility are guaranteed by the same program or whatever you have. But on the other hand, these products, the ones that today are on the market, are sound design oriented, are not fit for actual product development. Their size and portability is not good for product development as well, and their computational efficiency is not fantastic. There is another way, though. There is the language nerd way. Essentially, this is a programming language that we are developing inside my company. I'll never go into details here, but essentially here you can express things in a very, let's say, natural way and forget about the details. That's the point. So we use a restricted syntax and semantic, and these languages can follow various paradigms, each has its own, imperative, functional, data flow, whatever, and they can be used in different ways according to how the compilers on transpilers are made. Like transpilers means that you translate this code into the source code of another language, usually a low-level general purpose language. You can do just-in-time or ahead-of-time compilation. You can build front ends for compilers, whatever you want. So how do these compare to general purpose languages as well? They are conceptually simple and focused, so you don't start over-engineering, hopefully. They give you homogeneity by design. You can process sample by sample, usually using these sort of languages, but they take away flexibility, the flexibility that general purpose language give you. It becomes hard or impossible to import external code, so you're bound to the model that these languages provide. And the current products until yesterday are immature and look like research toys, and they're little known and used, and there is very limited tooling. A little bit further, let's go a little bit further into this stuff. When it comes to DSP, let's see what are the computational models in each of these approaches. For general purpose languages, it's this, there is none. You make up your computational model. When you use patcher-style systems, the patcher usually works on graphs, where each node of the graph is some box, and the interconnections are the interconnection between the box. So essentially, you technically have a directed acyclic graph, which is scheduled by the program for you, so you don't need to specify which thing is executed when, and it's built on buffer-based processing. If we look at domain-specific languages, usually you have another kind of graph that's a directed graph, which can be cyclical, as long as the feedback paths contain a unit delay, otherwise the things would be not computable. The schedule is built in an analogous way to the patchers, and processing usually happens sample by sample. And what is interesting is that this model is more general than the previous one. So in theory, you could develop a patcher that translates to a domain-specific language. So all of this to say, to explain how I think we can LEGOfy. How can we make this whole DSP development thing scale a little bit? For me, this is the answer. So essentially, we would have audio programmers do their work happily, without pressure, on the platform code, on the audio code, whatever is external, and interface with DSP code, and their job would stop there. Then we would have sound designers play with patchers and design tools, and DSP engineers being in the middle this time, dealing with both the same programs, the same, let's say, metaphors that the sound designers use, but also developing the DSP part in terms of reusable components developed in general purpose languages, and deal with domain-specific languages as well, which could be translated then at the end into general purpose DSP code. So, last part of this presentation, I will just tell you about what we are doing in our company to improve our output, both in quality and in quantity. We have developed an automated circuit analysis tool, which we call NetMix, and we will never share it with anybody, probably. It works like this. No, you will see, because it's kind of an advanced tool. It works like this. You input a SPICE netlist. For those who don't know, SPICE netlist is a representation of a circuit. And we annotate it manually in the sense that we say, okay, this resistor is actually a parameter, this other thing is to be computed like this, but it's still a SPICE netlist at the end. The program derives those circuit equations from the netlist, it discretizes them, and then interactively with you tries to collaborate with you to find a solution of the system of equations that come from this process. This is translated into the language that we've seen before, and then that language, the compiler of that language, translates this code into either C++, MATLAB, JavaScript, or D, and D was contributed by somebody. We have no interest in D, honestly. So, what is this language? This domain-specific language that we have developed is called Charamella. You can go on the website, try it directly there. There is a web tool, it works on the browser directly. It's a data flow domain-specific language. It's declarative, so it doesn't have any, you don't have to specify the order in which operations are executed. It will be up to the compiler to find the proper path of execution. It's extremely minimalistic. It's very, very modular. It's both an academic and an industrial project. We are collaborating with the University of Udine in northern Italy for the academic part. And it has, actually we have a transpiler written in JavaScript. And we use it as an infrastructure in the sense that this thing is not just hackable, it's part of it. For example, the code generation part is based on templates, and you can modify them or provide your own. Adding support for more formats and languages is extremely simple. And indeed, we had this D contribution, which we didn't do ourselves. And right now we have output formats, support for output formats for BST2 and web audio. Then, little announcement. We are also developing a library of reusable DSP components, which, unlike the other ones on the market, wants to be characterized by a large selection of algorithms rather than focusing on anything specific, which will try to enforce as much as possible minimalism and consistency. It's implemented in a precise way, so it's not random algorithms taken here and there. We are trying to prioritize over everything robust behavior rather than perfect sound, because we want people to be comfortable using it. It is extremely portable. It's written in plain C with no dependency on the standard standard math library, but not even a large part of the standard C library. We offer, it's open source, so it's already there online. You can go and download it and use it for your open source projects under the GPL license. But we also have a commercial licensing option if you want to develop your own commercial product. We hope to make extensive documentation. We have some API documentation already online, but we want to document it even further. And we offer support and custom development based on the library itself. So, last slide. Looking ahead, I think that we will ourselves try to follow this hybrid approach, combining many ways of reusing code together. And we would like to build an open source and hackable stack of technology that can be used for this, to help reuse DSP code developed in different ways. And we, of course, if it's open source, we want to do it with everybody who is interested. We would like to have developed tools for DSP development, debug analysis, so specific tools for the domain. We would like all of this to be extremely portable, simple to use. And we would like, and I cannot underline this enough, to stress on technology transfer. We really need to have researchers work with companies, in my opinion, in this field, because otherwise we will just lag behind. That's all.